All right, so apologize for being a couple of minutes late today. What we are going to talk about today are Zener diode voltage regulator circuits, digital logic, and clipping or limiting circuits. So let's start with diode-based digital logic circuits. Oh, and for those of you that are on Zoom, please say something in the chat so that I know that you're here. Four people. Great. The other three people, I guess, aren't paying any attention. So it goes. All right. So diode logic circuits. All right, so let's consider this first circuit. All right, so this is the first circuit that we're going to look at. We could have more or less inputs if we wanted to do so. So this is an example of a OR gate, okay? This is a diode-based OR gate. So let's talk about why it behaves that way, all right? So let's consider the first case. We're going to make effectively a logic table here. So VN1, VN2, VN3, V out. I need to turn off my email client, or that's going to get annoying. All right, so let's say that I had a digital low signal applied to each of my three inputs. All right, so 0 volts, or really any voltage that's less than VD on. What is going to happen here? Anybody got any ideas? Right, so if this guy is 0, 0, and 0, all three of my diodes are reverse biased. And so we could treat them effectively as an open circuit. So there is no current conduction path through the resistor, meaning that there should be no voltage drop over the resistor, and therefore V out is 0. Pretty straightforward. If I set Vn as 1, now Vn being a digital high, so really any voltage greater than VD on, This guy will be able to conduct current, my first diode, D1. Let me label my diodes, I guess, real quick. So D1 is forward biased, is able to pass current, which means their current will flow through the resistor R, and my output voltage will be non-zero. And that's going to be true for all other configurations of single diodes, as well as all configurations of multiple diodes. Let's see, 0, 1, 1 gives me 1, and 1, 1, 1 gives me 1 as well. So this is a simple diode-based OR gate. We could expand it to an infinite number of inputs, and it would still behave in the exact same way. As long as any one of the diodes, one or more of the diodes is forward biased, our output goes high. So fairly straightforward. For our AND gate, it's going to look something like this. D3. And here is our resistor R. Okay. So we have 3 diodes again. Notice that they're effectively flipped in polarity from the diodes of the OR gate. And so if we drew our logic table, let's talk about what's going to happen here. All right. So with all 3 of these diodes reversed biased, that means that the only current conduction paths in this circuit are through the diodes, right? So this 5-volt drop, if there's no current flowing through any of the diodes, then the current that flows through the resistor R is 0, and so our output is high, right? So what condition makes current flow through our diodes? So what conditions on our inputs makes current flow through our diodes? Right. So this is the cathode, this is the anode. So if Vn, we're assuming the ideal diode, or not the ideal diode model, the constant voltage drop diode model, right? So if Vn is less than, so let's see, I'm trying to work my way through this here. So we have 5 volts here. If this guy is conducting, current flows through the resistor, and the voltage here is lower than 5 volts, right? So if this guy is less than 5, this diode is forward biased, and the voltage drop over the resistor decreases, right? Or there is a voltage drop over the resistor. Does that make sense? Let's start there, right? So for those of you who are on Zoom, let me explain my logic for this logic gate. All right. So let's say that VN1 was digital high or 5 volts. Diode 1 would be forward biased, right? Which means current would be able to flow through here. Since there's current flowing through the resistor, the voltage drop at this node would not be 5 volts. And so our output would be 0. Same thing should be for any single diode being on. Only one is reverse bias. Hold on. I might be confusing myself here. What's drawn? Yeah. The A, B, and C should be positive voltage. All right. So, sorry, I'm just trying to make sure I'm making sense of this correctly, because to me, intuitively, this looks like a NAND gate, but it shouldn't be. All right. So let me think about that again real quick. So if VN 1, so if we put 5 volts here, this diode is forward biased. Current is going to flow through. Like so, which means there is going to be a voltage drop across our resistor and then across, all right. Right, using the constant voltage drop model here. So if Vn goes high, actually, let's not do that. There's no voltage drop over the resistor. All right, so sorry, I'm thinking my way through this. It looks like when the output should be 5 volts when no current is able to pass through all 3 diodes. So let's start there. Okay. Sorry. This is what you get for this being my first time teaching the class and having to think through these things. All right, so how do we make no current flow through all 3 of the diodes? That's the fundamental question here. All the inputs, if all the inputs are high, then no current flows through. So if all the inputs are high, then they're all reverse biased. Yeah, you're right. Okay. Let's erase these. So if all of the inputs are high, all three of the diodes are reverse biased, which means no current will flow through the resistor, and so V out is equal to 5 volts. If any diode becomes forward biased, then current will flow through the resistor, and V out will be lower than 5 volts. Yeah, okay. Zero, 1. Thank you, Pozniak, for being smarter with your digital logic than I am. Okay. So these are the two different logic gates that we can make with diodes. Simply AND gates and OR gates. So picking one of these, as one group already has, is a fairly straightforward design problem. The only thing that you really need to worry about is when you're using the constant voltage diode model, that's going to kind of skew what you're limiting your input signals to be. And there's some stuff about that in the project assignment description itself. All right, let's talk about something that I guess to me is a little bit easier to understand then, voltage regulator circuits. We've already briefly talked about a voltage regulator circuit by using multiple forward biased regular diodes. That was in the example problem I worked with the cell phone charging circuit, or the USB port charging circuit. But in general, so sometimes we need to supply a nearly constant, constant DC voltage to a load. So if we used a rectifier circuit and we were able to convert an AC signal into effectively a DC signal with a small ripple, what happens when we have a load that can't tolerate even that small ripple? Well, we need to use a voltage regulator circuit as well. So a very common configuration would be something like this. And this is a symbol that Dr. Batari is using that I actually kind of like. So this big diamond with a diode in the middle of it is just representative of a diode bridge, the exact diode bridge that we use in our full wave rectifier circuits. Here's our capacitor, which is going to give us a better approximation of a DC circuit. Here's a resistor. And then what we would do is we would put in a Zener diode. And this is the symbol for a Zener diode. And connect this to our load. Like so. So here's a basic voltage regulator circuit. We could actually break it down a little bit further into effectively a functional block diagram. So I'm going to call this guy VSS. VSS is the variable source voltage. All right. So in this circuit, VSS would effectively be here. It's some DC value with a small amount of fluctuation. Well, then we break this down into our voltage regulator circuit. And then this guy is in turn connected to our load. Where this is V load and this guy is I load. All right. So our voltage regulator circuit, this guy here, is really just this part of that top configuration. Here's V in, and here is V out. All right. So it's just a simple, almost effectively a voltage divider circuit from a small signal standpoint, right? From the small signal where we're trying to get rid of our ripple, this guy looks like lowercase v in our resistor R, and then the dynamic resistance of our Zener diode, and here we have lowercase v out. So the Zener diode operates in the reverse bias breakdown region. So effectively, if we looked at the curve for a Zener diode, here's VD and here's ID. And the forward bias region, it's going to look pretty normal. But in the reverse bias region, once we hit that breakdown voltage, we effectively start passing any amount of current that we need. So when current flows through, it's pinned at the, or when it's sufficiently reverse bias, effectively the voltage is pinned at one specific voltage or very close to it. So there is technically a slope to that nearly vertical line, but it changes with current only very, very slightly. So this voltage right here, V breakdown, which is a negative voltage inherently, is going to give us a near constant positive polarity voltage V breakdown like so. All right, so looking at our small signal model, what we want, or why it behaves this way effectively is we look at our small signal model. Times Vn. If R is much greater than RD, what happens even with a very large input voltage, so a voltage change? So let's say that for this circuit, RD is somewhere on the order of 1 ohm and R is 1 kilo ohm, and our ripple voltage was around 0.2 volts. What would our output voltage be? Yeah, so it would be 1 ohm over 1001 ohms times that 0.2 volts is approximately 0. That's how our Zener diode effectively pins our voltage to being a constant value. Okay. So one thing that's pointed out, not in the textbook that you guys have, but in the textbook that I used when I took this class forever ago, is that for a silicon diode, for whatever reason, a 6-volt Zener diode is usually the most stable. So let me see if I can find it real quick here. All right. The breakdown voltages of Zener diodes are temperature dependent. In general, silicon diodes with breakdown voltages less than 6 volts in magnitude display a reduction in breakdown voltage magnitude with increased temperature. So the hotter it gets, the worse it works as a voltage regulator, because the voltage starts to, the magnitude of the voltage starts to decrease. So instead of pinning it at 6 volts, it would go down to say 5.4 volts or so. Conversely, breakdown voltages greater than 6 volts tend to increase in magnitude with temperature, whereas breakdown voltages of about 6 volts tend to be nearly independent of temperature. Furthermore, the characteristic curve tends to be most vertical for Zener diodes with breakdown voltages close to 6 volts. Thus, Zener diodes with a 6-volt breakdown voltage provide the best performance as stable voltage references. Saying that, just to be very clear for some of you guys who may choose to do the 48-volt Zener diode voltage regulator project, means you just put 6 of them in, or no, 8 of them in series. So just a heads up, if you want it to be very stable, that's a way to go. All right, so before we move on here, I want to talk about 2 figures of merit for voltage regulator circuits. The first of which is what's called line regulation. And I'm going to put in parentheses source regulation. So the line or source regulation, they represent the exact same thing, is the stability of the output voltage with respect to input voltage variation. So this is simply delta V load divided by delta VSS times 100%. Then we also have another figure of merit, which is called the load regulation. And this is the stability of the output voltage with respect to load current variation. My thing will write load current variation, or delta V load divided by delta IL times 100%. So ideally, like in an ideal case, the regulations should be 0%. And what that means is there is no variation in the controlling variable. So if the load voltage doesn't change, which is what we're looking for with a voltage regulator, that's the most ideal situation as possible. So if VSS changes by a large amount while V load changes by a negligible amount, then that means we have very good line or source regulation. And if the load current changes by a large amount, but the load voltage does not, we have very good load regulation. All right, so voltage regulator circuits, fairly straightforward. Effectively, you're just using either, we only talked about Zener diodes here because we talked about using regular diodes to doing it in a previous example problem. But we saw that we could do a relatively large, so for the cell phone problem that we worked, we had a relatively large change in our input voltage of 5 volts or half a volt. And we saw, I think, only 65 millivolts of change in our output. So we had pretty good regulation there. All right, let's see what's in chat here. Just another person saying that they are here. All right. So our last topic of the day is a limiting circuit. All right, so let's consider a cell phone or really any antenna system, okay? So you guys have had, or you're currently enrolled in your electromagnetic field theory classes and you've had physics 202. So how do electric fields respond to distance? So let's say I'm very close to a source of an electromagnetic field. Is the signal strength going to be higher or lower than if I'm very far away from that source? It's going to be higher, right? So that means that the voltage present at my antenna on my cell phone or something like that is going to be at a significantly higher value. Well, that would mean that if there weren't such things as like limiting circuits, the closer I got to a cell phone tower with my cell phone, the more likely I would fry the internal circuitry of my cell phone because I'm too close, right? So my voltages could potentially exceed the ratings of the components inside. So we can use diodes to limit the circuit in order to force a particular voltage drop to occur. So let's take a look at this particular circuit like so. Here we have Vn of t, and let's say that Vn of t is 15 sine omega t volts. Here is a 2 kilo ohm resistor, and then we have a diode and a battery. And let's say that this battery is 6 volts. And then we have over here another battery. This guy is 9 volts. And a subsequent diode with this orientation. And lastly, over here, we have our voltage. All right, so this is an example of a limiting circuit. So let's assume that we are using the ideal diode model here. All right. So here's voltage, here's time. I'm going to do my input signal in blue, I think. Like so. All right. So for the positive half cycle, I'm going to let me label some diodes here. Here's diode 1, and here's diode 2. So for the positive half cycle, it hopefully is intuitively obvious that D1 is on or forward biased, and D2 is off or reverse biased. So let's start by making sure that we agree that that's the case. Anybody have any questions, comments, or concerns about that not being how things are working? So we're saying D1 is on, D2 is off, right? Because this potential should be higher, so when D1 is larger than 6 volts, this guy is on. Let's say that. So when D1 is higher than 6, this guy is on. And when D1 is less than 9, this guy is on. When these diodes turn on, we have a short circuit. So what that's going to do is anytime the input voltage is greater than 6 volts, it's going to pin the output to this voltage of this battery. And anytime Vn is less than -9 volts because of the polarity here, our output's going to be pinned to -9. So our output should look something like this. Let me draw a scale here. So this is 15, 9, 6, 3, 12, -3, -6, -9, -12, -15. All right. So what should be happening here is our output follows our input until diode 1 turns on, clips it. When Vn starts falling below, follows it again until we hit -9 volts, and then clips it again. And this is going to happen over and over and over. So the diodes in series with these batteries forces our output to stay between these two specific values. Now, what happens if we don't have batteries readily available? What could we do? We could replace our batteries with Zener diodes because they have effectively the same characteristic. They're going to pin it to a specific voltage. So Here's diode 1 again. Here's Zener diode 1. Zener diode 2. Diode 2. This guy should have effectively the exact same input-output relationship, but we can actually go one step further in simplifying this guy. Oh, well, actually, before we start, we could specify, assuming the ideal diode model, 6 volts, 9 volts. This is the most simplified version of our circuit. So we don't actually have to use regular diodes in here at all. We can do everything with just these two Zener diodes in series, but with the anodes connected to each other to get the exact same results. So clipping circuits like this, these are really what they're called, are used in a wide variety of applications. In limiting circuits an awful lot, but the place that I personally saw them first is the output stage of a guitar's distortion pedal. So effectively, what something like this does, if you have an effects pedal and you feed in a sinusoidal signal of a certain scale, what this guy does is it cuts off the tops of your sinusoidal peaks, both the positive polarity peak and the negative polarity peak. If you use the same diode, that would be what's called symmetrical clipping, and it gives one particular sound, which isn't a true sinusoidal tone to your ears. Or if you put, say, one diode, so symmetrical clipping, is something like this. Here's R, D1, D2, where D1 and D2 are the same thing. Here's VN, here's V out. Asymmetrical clipping. Similar, but you would have, say, one diode and then two diodes on the other side. And so what asymmetrical clipping does, draw a picture here. So it clips the same amount on either side, whereas asymmetrical clipping is more like the example that we did a moment ago. So where one side might only get 0.6 volts at a maximum, the other side would get more. So it's not truly sinusoidal, but you get a more sinusoidal waveform on one half of the cycle than the other. You can also accomplish asymmetrical clipping just by using two different types of diodes, or some modern effects pedal makers like Brian Wampler and stuff like that have started using different colored LEDs inside their effects units to do asymmetrical clipping, because different colored LEDs and I mean true different colored LEDs, not it's an LED with a green cap, a green plastic cap on it to make it give green light, like a real LED that emits green light versus an LED that emits blue light, have different characteristics, and so they'll give you asymmetrical clipping. Okay, so that's all I've got for PN junctions and diode circuits. So real quick, we've got 20 minutes left or so. I want to pop over to Moodle here and point a couple of things out. I have, you can see on the left-hand side here, I've done a little bit better job of organizing things. I have the videos uploaded to here, I think, and I'll get the rest of these uploaded today. In the Project 1 section, there is the project descriptions, which we talked about briefly the other day. Those are uploaded for you guys. And then there's also this guy, which is effectively a rubric telling you what I want. Okay. Let me make this guy bigger. So it says each group will be given one circuit design problem emphasizing the application of diodes. The goal of this problem will be to convert a given input signal to a specified output signal, which all of that's detailed in the project descriptions. Each group will receive a document describing the input signal's characteristics and the requirements of the outputs. Groups might have additional design requirements explicitly pointed out. This document is already uploaded on Moodle, as it is. In addition to the input-output conversion, the student should attempt to identify and account for other design parameters that affect the feasibility of their design, such as, but not limited to, component non-idealities, component tolerances, component availability, and power consumption and dissipation. So what we really mean by that is you're designing this circuit and you're going to be simulating it entirely. We're not expecting you to be able to go to Mauser or digikey.com and buy the parts and put it together. That being said, your design should use practical component values. So for instance, if you design it for, if you design a circuit, I don't want to see that it's going to use a 137 ohm resistor, because a 137 ohm resistor does not exist. Or if you could buy it, it would have to be a custom ordered thing. And so for instance, 130 ohm resistor, I think, is a standard value, probably costs somewhere around a nickel. If you wanted to get a custom made 137 ohm resistor would probably cost somewhere on the order of $8 to $10, right? So I want to see that you're taking into account the component values that you use for your circuit design are things that are widely available and we could order and all that kind of good stuff. Also take into account power ratings and things like that. So if you used a 1/4 watt resistor and your circuit analysis, simulation circuit analysis tells you that the resistor is going to be absorbing 2 watts of power, what does that mean? You chose a poor choice of resistor because you would burn it out. So just take things like that into account. Start considering the actual practical application of some of the analysis and theory that you've learned. That's really what we're harping on here. Because if we get you in the practice of it now, when it comes down for senior design next year, you're not going to waste a ton of money blowing stuff up. So it's good to start thinking about those kind of things right now. All right, the general design process is to follow these steps, identify the general requirement of the circuit. So what are you actually being asked to do, which is usually specified extremely well in the project descriptions. If you don't feel that you have enough information, look at other things, research the topics, or feel free to ask me a question. What is required of you is to formally compile a list of the figures of merits and secondary requirements, such as size and power requirements, and spend some time analyzing the priority. Now, your solution. Analyze a simplified design, so use the ideal op-amp model to kind of make sure things are going to behave the way that you expect them to behave. Run a couple of simulations. Make sure everything's working right. Then start making notes about what elements are critical to the requirements. So for instance, it says here, make a note of the max reverse voltage applied to any diode of your circuits. And that is because if you choose a diode off of a sheet and you're regularly exceeding the maximum reverse bias breakdown voltage, assume that that diode is going to work how you think it's working, because you're constantly effectively burning it out if it's an avalanche diode. And then finally, do a SPICE simulation of all that kind of good stuff. Then be thorough in your discussion of how your circuit behaves. Use theory, background, all that kind of good stuff. Effectively demonstrate your technical knowledge based on what we've learned in this class. In each report, the design process should be documented. Use the design guide as an outline for your report. You don't have to and probably shouldn't call the sections given required solutions and discussion. So more typically, it would be background, methods, results, and conclusions. When writing this report, you're supposed to convince me that you followed the above process. You want it to be clear that you spent time understanding the problem solutions. It's okay if you can't completely satisfy the requirements that you identified, but you need to make me aware of that and you need to explain why. And then there's no particular page requirement. If you accomplish the goal of writing the assignment, then you're done. Visual aids are important. So what that means is feel free to use circuit schematic diagrams and things like that to help illustrate your points. I don't want 4 pages of just straight text because I'm not going to read it, to be entirely honest. I like pretty pictures. All right, and then here is the weight distribution for the different parts of your things. So students demonstrate basic knowledge of SPICE simulation is 1/6. Students understand relevant equations and principles and can apply this knowledge is 1/3. Students can effectively communicate their design process and results is 1/4 of the total points. And students have considered the practical consequences of their design choices is another 1/4. So does anybody have any questions about what I want of you and how this will be graded? I might try to, over the break, write up one for one of the projects that Prashana and I decided to toss out to give you guys a formatting example and all that kind of stuff. Depends on how much of my break I want to spend actually working. Probably pretty little, but I feel like I could knock something like this out in an hour or two. So any questions or anything, you can ask them now, ask them over the break, whatever. Still haven't conferred with Dr. Batari about when the exact due date will be, but again, my best guess would be the week after we get back from break. So sometime in the January the 11th region. Okay, so nobody has any questions about this. One other thing I wanted to point out, Dr. Batari gave his class a bonus quiz today because so many of you guys are showing up online. That was hard for me to do, and I also showed up a little bit later to work than I wanted to because I was working on putting something up on Moodle. So what I'm going to do is I'm going to put a bonus quiz up in this section where it says bonus quiz that is currently empty. It will be timed, meaning you will have 15 minutes to complete it. It will be 5 theory questions, extraordinarily similar to what should show up on your exam when you get back, like potentially literally the exact same questions. So it's good to know this. I'm going to let this quiz be open book, notes, etc., because I don't really feel like setting up respondus and all that jazz for this. So this bonus quiz will have 5 questions for a maximum of 5 points. these 5 points will be applied towards your exam 1 grade. So that means since exam 1 is 24% of your grade, these 5 points on that is, I believe, effectively potentially 1.2% of your final grade just being given to you by taking a 15 to 20 minute open notes, open book quiz. So I'll get this up sometime probably today or this weekend, and I'll allow you to do it anytime over the break. I'll probably set the due date for it to be midnight on January the 4th, so the day we get back. So for those of you that totally forget to do stuff over the break, it'll be available for you to do on that Monday as well. Because I know a lot of you, if this is your only class, you were leaving and getting the hell out of here. I know as soon as 12:30 comes and I'm out of my second class, you will not see me until January. So, all right, any questions regarding any of this jibber jabber? Problem 3 on the web work. All right, let's pull up web work here. Let me find my keyboard. Winter 2021. Which homework set? Homework 3? Homework 3, problem 3. The 3 series diodes in the above circuit carry a current of 7 milliamps. The load consumes a current of 20 milliamps. If the load current increases by 20 milliamps, what is the change in the regulator output voltage? Okay, so the 3 series diodes carry a current of 7 milliamps. The load consumes 20. And the load current increases by 1 milliamp. What is the change in the regulator output voltage? All right, so how I would approach this, we're not given a specific VD on to worry about. Let's go back to homework 3. Let me see if we're told anything specific here that I'm overlooking. Because my instinct on this particular problem would be to treat it very similarly to the voltage regulator circuit that we analyzed with 6 of these bad boys in series. Okay, problem 3. Nowhere does it tell us. So my concern here, we're not told VD on, and we are not told IS. If we were told VD on, then we should be using the constant voltage drop model. If we were told IS, we would be using the exponential model. If the load current, the load consumes the current. We're not given power, so we can calculate the voltage drop of the regulator either, because that could help us. Honestly, I'm not sure. Shoot me an email and I'll talk to Dr. Batari about this to make sure I understand what's going on, because it seems to me like it's missing some small piece of information somewhere. Doesn't even give us a value of that resistor so that we couldn't use that to figure out exactly what's going on. the dynamic resistance is VT over ID. So we know the dynamic resistance of these guys. We have a small yeah, I feel like there's one, I'm overlooking some trivial piece of information here, so email me and I'll get back to you. I have an idea, but I don't know if it'll pan out because of what I think I'm missing. So just be straight up with you. Not entirely sure how to approach this. All the other problems looked okay though, let's check. So this is a simple limiting circuit, very similar to the one we did, except that instead of using the ideal diode model, now we're using the constant voltage drop model, so that should be fairly straightforward. That's the one I'm going to question about. This is determining C for a half-wave rectifier circuit with a lot of things provided to you, so I think that one's probably for, yeah, just the formula. And the first problem, find the ripple based on all those parameters, so it's also just the formula. All right, so problem 3 is the only one that's remotely tricky. All right, I will happily take a look at that and get back to you. Yep.